Bismillah ar-Rahman ar-Rahim. This video is about the integral from 0 to pi over 2 of the product of the natural logarithm of 2 sine x over 2 and the natural logarithm of 2 cosine x over 2. We want to prove that the integral of this product is minus pi cubed divided by 48. Let's start by developing the tools needed to evaluate this integral. The Taylor series expansion of the natural logarithm of 1 minus z is minus summation m from 1 to infinity z to the m over m. This is true for any point on or inside the unit circle in the complex plane, except when z is exactly equal to 1. Let's investigate the sum g from 1 to infinity, z to the j divided by j squared. This is the dilogarithm of z, but we are here more interested in the sum itself. If we take this sum and add 1/2 times the square of ln 1 minus z, we get the dilogarithm plus 1/2 the square of the sum, which is a double sum, summation k from 1 to infinity, m from 1 to infinity, z to the m over m times z to the k over k. That's z to the m plus k divided by mk. Let's change the summation index k to the summation index j. J is m plus k. K is j minus m. Because the two indices here start at 1, then j starts at 2. J is the sum of the two indices. So j is strictly greater than m and j is strictly greater than k. Our new double sum has the index j from 2 to infinity and the index m from 1 to j minus 1. The summand itself becomes z to the j divided by m times j minus m. 1 over m plus 1 over j minus m is equal to m times j minus m in the denominator. In the numerator, we have j minus m plus m. This is j divided by m times j minus m. This means that 1 over m times j minus m can be written as 1 over j times the sum of 1 over m and 1 over j minus m. This double sum can be written as such. And from the first sum, we can separate the term corresponding to j equal to 1. This is z to the 1 divided by 1 squared, that's z. And then we have the same sum, but starting at 2. Let's combine these sums. We have summation j from 2 to infinity, z to the j divided by j. To get this guy here, we need 1 over j, so that we get z to the j over j squared. Then from here, we have 1/2 summation m from 1 to j minus 1 of 1 over m. Then we have 1/2 summation m from 1 to j minus 1, 1 over j minus m. Note that this sum is 1 over 1 plus 1 over 2 all the way to 1 over j minus 1. This is by definition the harmonic number hj minus 1. What about this sum here? When m is 1, this is 1 over j minus 1, and then 1 over j minus 2. When m is equal to j minus 1, we have 1 over 1. This is again the harmonic number hj minus 1. These two sums together, after multiplying by 1/2, give us hj minus 1. hj minus 1 plus 1 over j, this is the jth harmonic number, the sum of the reciprocals of the positive integers from 1 to j. The dilogarithm of z plus 1/2 times the square of the logarithm of 1 minus z. This left-hand side is equal to z plus summation j from 2 to infinity, z to the j divided by j. Then we have the jth harmonic number. This lonely term here can be written as z to the power 1 divided by 1 times the first harmonic number h1, which is just 1 over 1, which is 1. In other words, we can take this z and join it to this summation. So the sum from 1 to infinity using index small n of hn divided by n times z to the n is equal to the dilogarithm of z plus 1/2 log 1 minus z squared. We will need this result later. Now let's do some Fourier series work. We have the function 1/4 times x squared minus pi squared over 12. At x equals 0, this is minus pi squared over 12. The function increases to pi squared over 6 at minus pi and pi. Take this curve and shift it to the left and to the right by all integer multiples of 2 pi. This way, we construct a 2 pi periodic even function. Because the function is even, its trigonometric Fourier series has the form a0 plus summation n from 1 to infinity an cosine 2 pi n over the period, which in our case is 2 pi times x. The coefficient a0 is 1 over the period. Then we integrate over a period. Let's say we will integrate from minus pi to pi, 1/4 x squared minus pi squared over 12. This yields 0. The coefficient an for positive integer n is given by 2 divided by the period. Then we integrate over the period the function times cosine nx. If we carry out this integration, it gives us cosine by n, which is minus 1 to the power n divided by n squared. The integral can be carried out via integration by parts as written here. When x is from minus pi to pi, our function f of x 1/4 x squared minus pi squared over 12 is given by a0, which is 0 in our case, summation n from 1 to infinity, an times cosine nx. We also need a shifted version of this identity. Replace x on the left-hand side and right-hand side by x minus pi. In this case, we get an expression that is valid for x between 0 and 2 pi. This x squared becomes x minus pi squared. We also have x here, cosine nx minus pi. This is cosine nx times cosine n pi. Cosine n pi is minus 1 to the power n. These two guys together are equal to 1. So we get the identity that summation n from 1 to infinity 1 over n squared cosine nx is equal to minus pi squared over 12 plus 1/4 times the square of x minus pi. X is between 0 and 2 pi. Let's go back to our first derived result. The summation on the left-hand side with the nth harmonic number, and then the dilogarithm of z, and this 1/2 of log 1 minus z squared. Set z equal to e to the I x, where x is in the open interval from 0 to 2 pi. So z is not equal to 1. If we do this substitution on the left and right-hand sides, we get this expression here. Let's focus on the logarithm. The natural logarithm of 1 minus e to the I x can be written as the natural logarithm of e to the I x over 2. We have 1 here, so we need to have e to the minus I x over 2 minus e to the I x over 2. We know that e to the I theta minus e to the minus I theta over 2i is equal to sine theta. This difference here can be written as minus 2i times sine x over 2. The argument of the logarithm is 2 sine x over 2 times minus I times e to the I x over 2. This minus I can be written as e to the minus I pi over 2. These two exponentials can be written together as e to the I x minus pi over 2. The logarithm of the product is the sum of logarithms. Thus we get the logarithm of 2 sine x over 2 plus the logarithm of e to the I x minus pi over 2, which is I times x minus pi over 2. Here we are using the principal branch. We can square the logarithm and square the sum of these two terms to obtain this result here. So summation n from 1 to infinity hn over n e to the I nx is equal to sum n from 1 to infinity e to the I nx over n squared plus 1/2 the square of the natural logarithm of 2 sine x over 2 minus x minus pi squared over 8 plus I over 2 x minus pi log 2 sine x over 2. Our next step is to take the real part of this side and equate it to the real part of that side. On the left-hand side, we will have the summation with the nth harmonic number. The real part of e to the I nx is cosine nx. The real part from here will be summation n from 1 to infinity 1 over n squared cosine nx. This term here is real. Note that x is from 0 to 2 pi, so x over 2 is between 0 and pi. Thus sine x over 2 is strictly positive. Then we have minus 1/8 of the square of x minus pi, and this term goes away when we take the real part. Now we make use of the Fourier series result on the previous page. Specifically, this summation here, n from 1 to infinity cosine nx over n squared, when x is between 0 and 2 pi, is equal to 1/4 times x minus pi squared minus pi squared over 12. Using this result, 1/2 times the square of the logarithm of 2 sine x over 2 is equal to this summation involving the nth harmonic number minus 1/4 x minus pi squared plus pi squared over 12 plus x minus pi squared over 8. We can combine these two guys to get this result here. Now we have an expression for 1/2 times the square of the natural logarithm of 2 sine x over 2. This function can be written as the constant pi squared over 12 minus 1/8 x minus pi squared, and then this infinite sum here. We need a representation like this, but for the logarithm of 2 cosine x over 2, and the way to obtain it is to go back to our first result, and now we set z equal to minus e to the ix, where x is between minus pi and pi. We do similar steps like above The natural logarithm of 1 plus e to the ix can be written as the natural logarithm of e to the ix over 2. Then we need here e to the minus ix over 2 plus e to the ix over 2. This time, rather than getting sine, we get 2 cosine x over 2. This logarithm is equal to log 2x cosine x over 2 plus ix over 2. If we square both sides, we get the square of the logarithm. We get I squared times x squared over 4. That's minus x squared over 4. And then we get 2 times this term times that term. This is ix log 2 cosine x over 2. Taking the real part of both sides, this and that become cosine nx. From here, we get this square divided by 2, and we also get minus x squared over 8. This is an old friend, the Fourier series of 1/4 x squared minus y squared over 12, as obtained on the previous page. We can use this result to express 1/2 times the square of the logarithm of 2 cosine x over 2. We have minus x squared over 8, y squared over 12, and we have this summation with the nth harmonic number and cosine nx. Recall that our objective is the integral from 0 to pi over 2 log 2 sine x over 2 times log 2 cosine x over 2. What we have right now is a representation for the square of this logarithm and another representation for the square of that logarithm. To achieve our goal, we make use of the simple fact that alpha times beta can be written as 1/2 of alpha plus beta squared minus alpha squared minus beta squared. This is exactly what we will do here. We can express this product of the two logarithms as 1/2 of the sum squared minus the sum of squares. Of course, this trick makes sense and is useful if actually the integrals with those terms are manageable. So what if we integrate 1/2 of the sum of the squares? If we sum these two expressions, we get the following terms. We can easily integrate those guys from 0 to pi over 2. What about the series? Note that when we combine these two sums, we get 1 plus minus 1 to the power n, and this is 0 for every odd n. When we integrate, and assuming that it is valid that we can carry out the integration term by term, we need to evaluate integral from 0 to pi over 2 of cosine nx dx. This gives sine by n over 2 divided by n. If we look here, if n is an even integer, then we have sine an integer multiple of pi, which is equal to 0. That's very good. If n is even, this gives us 0. If n is odd, 1 plus minus 1 to the power n gives us 0. In other words, this summation disappears if we integrate from 0 to pi over 2. The integral of the manageable terms yields pi cubed over 24. To finish off our plan, we also need the integral of the sum squared. We need 1/2 integral from 0 to pi over 2 log 2 sine x over 2 plus log 2 cosine x over 2 all squared. We can combine these two logarithms. Together, they give us log 2 times sine x over 2 times cosine x over 2. 2 sine x over 2 cosine x over 2, that's sine x. This integration we have right here is 1/2 integral from 0 to pi over 2, the square of log 2 sine x. We have a representation of log 2 sine x over 2. This is valid for x between 0 and 2 pi. What we can do is to replace x by 2x and get an expression for this integrand, which is valid from 0 to pi. And that's okay because we are integrating from 0 to pi over 2. Can we integrate this from 0 to pi over 2? These guys are manageable. What about this series? The integral from 0 to pi over 2 of cosine 2nx is sine pi n over 2n. And this is 0 for every integer n. Again, we will say goodbye to the infinite series. The other terms give us pi cubed over 48. So this integral here, which is the integral of the square of this sum, is pi cubed over 48. Then our integral of interest is pi cubed over 48 minus pi cubed over 24. This is minus pi cubed over 48.